Hello everybody and welcome to this webinar about optimization of an impeller using our cloud HPC feature. Thank you all for being part of this webinar, for joining us here on YouTube. I see quite a few of you are still joining. So in the meantime, I start with the webinar itself. I start presenting myself and my company. So before actually I start, I give you a small advice. We have a chat on the right hand side. As the talking of the webinar is going forward, I'll keep an eye on the chat. So anytime you can make a question to myself or to other people here in the presenting the webinar, we will be happy to reply to you. There is also a poll. You can take part and somehow interact with us in order to decide what our next webinar is going to be about. So I just present the company. I am Ruggero Poletto from CFD FEA SERVICE. We are an engineering company founded in 2018. Our headquarters is in North Italy, near Verona. Our services are split into three different areas. The one is software development, in particular as far as the engineering application are concerned. Second topic is the cloud HPC, one of the tools we are going to see later today and have a look at how it can help us designing an impeller. And obviously we do consulting and engineering design activities for companies. So what is Cloud HPC? Cloud HPC is a cluster we can use in order to execute our engineering simulations. The particular things about this cluster is that it is available on the cloud. So we don't have the in-house infrastructure, but the infrastructure is on the cloud. It is available over the internet, okay? And thanks to this, it is possible to have a highly fidelity infrastructure, so avoid downtime. We continuously upgrade the hardware of the infrastructure, so at any time it is possible to have the most recent hardware. And also we continuously upgrade the software installed on the infrastructure, both in terms of type of software and also in the terms of version of software. The benefits of having the infrastructure a cluster for the CFD for the engineering simulations is in particular the speed up of the simulation. We can use a much higher number of hardware resources in order to compute one single simulation, or we can run several simulations at the same time. We just need to focus on our product. We don't need to worry about hardware resource maintenance, hardware resources security of the hardware resources. And another advantage is that we just pay for what we use. In a cloud HPC infrastructure, it's like we are renting the infrastructure based on a hourly rate. So we don't need to buy the server into our system, so make an investment. We just rent it on the go, and we also can rent licenses as we actually use them. Okay, so we don't need actually to buy software. We're just renting resources, hardware resources and software resources for what we are actually using. The software which are currently installed on the infrastructure, well, it's difficult. This is today's picture. As the time goes by, the number of software installed keeps increasing. We have Blender, Calculix and Codastar. Well, Blender is famous for rendering in general. Calculix and Codastar are well-known software as far as structural analysis are concerned. We have FDS and OpenFOAM. They are two very popular software in CFD analysis, so in computational fluid dynamic analysis. And today we're going to see a peculiar case in which we're going to use OpenFOAM. Then we have ParaView, which is quite common in post-processing. We have Vento, but many others are not mentioned here, and they are present in the platform. We have Salome, we have Shilab, we have CFMesh. So just refer to our website in order to get more detailed information about the most recent software installed on the platform. The main feature of the cloud HPC we produced is obviously the scalability. It is possible to run several simulations at the same time. So, and this is we call horizontal scalability. So various simulations, various scenarios at the same time performed simultaneously. Or it is also possible to have a vertical scalability, so run a simulation which is bigger and bigger in terms of mesh size, so in terms of hardware resources required to just compute one single simulation. This vertical scalability can be achieved both by using OpenMPI or OpenMP. So this depends actually more on the software you're using. So OpenFOAM in our case is just able to use OpenMPI, and we're going to see how we can handle this in OpenFOAM. Every simulation can run on up 224 virtual CPUs. Okay, so you have quite a few hardware resources you can allocate for just one simulation, and then you can run several at the same time. So that's the main feature. Obviously, we have connectivity. We're going to see the VNC connection, so a remote desktop into the running analysis, which allows us to run to use ParaView as post-processor. Or it is also possible to SSH connect to the simulation, which is currently running. We have a full set of API available, which allows you to interact with the simulations that we are running. I here report to the guide or manual page you can visualize in order to have an overview of the API system. And there is a Linux integration. So on Linux there is a package available at this link you can download and install on your Linux system. And this package allows you to execute and control the cloud HPC directly from your Linux terminal. And obviously it is possible to have support time from 9 to 6 European Central Time, summer or winter, depending on the season, let's say. And so there is a chat. You can ask for help at any time during this time range. So let's have a look at the example I was planning to see together today. So let's start talking about 3D parametric drawings. For this example, I used Solid Edge. It's a commercial CAD software, which can be used in ordered manner in order to generate a parametric CAD. In here, I generated an impeller. This is an impeller. It's made only by surfaces. Okay, so this is actually, it is still a 3D CAD, but it is just made of surfaces. And then I made 3D bodies just to overview the inlet and the impeller outlet. Okay, so all the wing, let's say the starter part of the impeller, and then the outlet, which is placed here at the top. Well, the main advantage of using 3D CAD is the fact that you can just change a variable and automatically upgrade your geometry. So let's just have a look at that. You see over here you can access the several data I used in order to draw the CAD or the impeller. If let's say I just want to increase the number of blades of the impeller, well, I just need to go to the pattern over here. 1 second, I need to reduce the size of the window. And instead of 10, I just select 8 impeller blades. And as you can see, the number of blades got reduced. I now modify it back to 12. And from now, I see I doubled the number of blades. As I did that, it is also possible, for instance, to modify the shape of the impeller. Okay, as you can see, I use this parameter just to tell how large is the impeller. If you want, I can expand it to 30, and now the impeller blades are longer, or I can reduce it to 10, and now the impeller blades are going to be shorter. But I can also interact on the angles. For instance, the attach angle of the impeller, I can increase to 30 degrees or can reduce it to 10 degrees. Okay, in this way, it's very, very easy to generate a parametric CAD. All you need to do is actually make drawings and make sure you have correct sketches, and you are quoting angles and you are quoting dimensions of your sketch. In this way, it is possible to have a parametric CAD from which it is easily possible to generate several geometries of this impeller. Well, I exported in here and imported in Salome the geometries I generated, and out of this geometry, okay, there is the inlet and outlet part. I can hide them. I just generated 6 impeller types. I generate a default one, which I called impeller 0, and then I generated a new one, which with a lower amount of blades. I generate a second one with a higher number of blades, a third one which the blades were longer, a fourth one with shorter blades, and a fifth one with a different angle of attack of the impeller. Okay, so in this way, it is possible to actually visualize my simulation. Okay, so the simulation overall is going to be made by 3 parts. There is an inlet over here. I try to visualize it. Sorry, it's this one. So this is the one highlighted right now is the inlet. There is obviously an outlet, which is actually this surface over here. And we have an impeller. We actually have several of them, and we are just replacing this central impeller into the meshing, which is going to be made with Snappy. Okay, so we just replace these 6 impellers in order to generate several meshes in order to compute our simulations in different geometry conditions. Okay. So all I have to do, starting from this, let's say, generated files from our CAD software, I just now move to the terminal. I hope you are all familiar with the terminal. If you're not, probably it's worth a while making a training of OpenFOAM, because OpenFOAM can only be controlled through the terminal. Okay, so that's important to know. In here, I exported under the STL folder. I exported obviously all the basic STLs of the geometry, so the inlet, the outlet, the wall at the inlet, the wall at the outlet, but I also exported the STL files of the 6 impeller configurations. Okay, so using these STL files, I just generated these impeller configurations, and that's what I'm gonna need in order to generate all the geometries. The other 2 folders are generated are one called mesh, which represents the input data for SnapPX Mesh. I don't know how many of you are familiar with that, but SnapPX Mesh has a certain configurations of how to give the geometry. Actually, let's do a step back. SnapPX Mesh is the mesh generator provided with OpenFOAM, and it has a certain type of syntax in order to pass to Snappy the geometry file into STL format, and to tell what is the cell number and cell configurations Snappy needs to generate. So in this general Snappy file, I just told Snappy I'm gonna pass him an impeller.stl file, an inlet, an outlet, and the wall. Okay. and obviously it also needs a rotor file. This rotor is important because it represents the rotating part of my simulation. Okay. So using that, I'm generated a sort of template of simulations which is going to be repeated again and again using all the impeller geometries we saw before. So we just need to replicate this template of a mesh with impeller 0 for the first case, impeller 1 for the second case, impeller 2, impeller 3, impeller 4, impeller 5 for all the impeller geometries we generated. So what I did is actually set up a template of mesh, and into this template I just replace the geometry file with the several STL files coming from the geometries configuration of the impellers. Okay, so this is important to understand, and please, if you don't, I just repeat it again. I just generated a mesh template file for SnappyX mesh. This is let's say a procedure to generate the mesh using Snappy. And into this template file, I'm just going to replace the geometry, the input geometry, with the several impellers which need to be computed, okay, in order to get the performances of these impellers. So in here, I just created a make mesh script. This is a bash script. It's quite simple, okay. So this mesh script takes an input array which lists all the configurations of the impeller we want to run. So we want to run impeller configuration 0, 1, 2, 3, 4, and 5. By looping into this array, I'm just copying the template folder, the mesh template folder, into an impeller minus E, impeller minus 0, impeller minus 1, into an impeller folder. And by entering this impeller folder, I just replace the geometry of the impeller. So I just replace the local impeller STL file with the one into the STL folder, into my repository of impeller. Into side of the STL folder, I have all the 6 impellers to be replaced. Okay. This is one of the trickiest part. I know some programming skills are involved into this situation, but I mean, I'm here actually to explain the steps. I repeated it a second time in a bit, but it's important to understand that this command just copies an impeller file available under the STL repository folder into the local folder, okay, of the let's say of the impeller mesh to be executed. Eventually, we have this command over here, which is a very basic command. It is used to execute the command on the cloud HPC. Okay, so this tells execute the SnappyX mesh command on a 16 virtual CPU machine on the cloud HPC, okay, and execute the mesh. So once again, let's have a look at what's happening here. This is a list of all the impellers to be executed, so from 0 to 5. In here, step by step, we are looping among all the impellers to be executed. We copy the template of the mesh to be generated into a custom one, so impeller 0, impeller 1. We enter that particular folder we have just generated. We copy the STL file from the STL folder repository of the impeller, and we replace it to the local file to be generated in the current case, and we execute the mesh on the cloud. Thanks to this, we can execute 5 meshes at the same time using, let's say, one single command. So I just save and close the script, and I just execute it by clicking /make mesh. So as you can see, step by step is going to go through the mesh execution 1. Actually, it's mesh execution 0. So that is going to automatically upload on the cloud the mesh. Sorry, I was wrong in here. And then automatically is going to execute mesh 1. If you see, as this process is like in execution, what's happening is that Impeller 0 is generated, Impeller 1 is generated. If I now refresh, is going to be generated also Impeller 3, Impeller 2. And step by step, we are generating Impeller 3, Impeller 4. These are the folders in which we are replacing the template with the custom Impeller STL files. And then we execute everything on the cloud HPC. So we just wait a little bit for this execution to be over, and then we enter our cloud HPC link in order to actually see these meshes which are in progress. Okay, it's nearly done. Now we are executing the last mesh. So if I just refresh, in here I can actually see that I generated the 5 impeller. You see the script execution is over, and I now go into my account of Cloud HPC. If I enter the storage, I can I just need to enter using obviously my credentials, username and password. In the storage, I can now see the 5 meshes which have been uploaded, and under simulation, sorry, I can actually see that these 5 cases are now in running. Okay, so that's one of the advantages of Cloud HPC. I can run simultaneously 5 simulations and have a look at what is happening right. How can I say? In one single look, in one single time. I don't need to generate these 5 meshes one after the others. Well, let's just now enter one of them. It's worth a while. Keep in mind that every simulation is performed on a virtual machine which is dedicated to that particular simulation. So it takes 2 or 3 minutes to actually allocate that virtual machine, and when this is allocated, actually the real mesh is going to be computed. So let's wait 1 more minute for this, let's say, virtual machine to be fully allocated, and then we will be able to actually see the mesh to be while it is in the computing phase. Yeah, that's one of the things. Let's enter the second one, which appears to be a little bit forward in the execution, a little bit ahead. Well, it's starting actually. It's about to start. You see now we have a remote desktop activation. Well, if I now refresh this page right now, here at the bottom, I can actually see the remote desktop. Okay, this is the remote desktop of the virtual machine when actually the mesh is computed. Okay, I don't need to take care about the sequence of the operations to be computed, like block mesh, SnappyX mesh, because this is automatically made by Cloud HPC. I just have to make sure that I configure correctly into the system folder the block mesh dict file and the SnappyX mesh dict file as well. At least these 2 files need to be correct. Using the remote desktop, I can double click, I can actually control everything that is happening over here. Okay, and the sequence of operation, as you can see, is block mesh dict, surface feature or surface feature extract, decompose par, and then SnappyX mesh. So the mesh is generated using the physical core which are present on the machine, and it takes a few minutes to be computed. So we just need to wait a little bit for the mesh generation to be over. As the 5 meshes are going to be computed, I move forward a little bit into explaining the next script. because the first script was the make mesh. The second one to run is run CFD. Okay? Once again, this script is kind of similar to what we saw before. Okay? It refers to the CFD folder. Okay? And it is just a loop among all the meshes, all the CFD this time to be computed, okay, and it just enters a directory and it computes all the CFD one by one, okay, linking that to the mesh which has been previously calculated. So on the cloud, we're going to have a CFD1, CFD2, CFD3 folder, and that folder is going to get the mesh from the Impeller mesh 1, 2, 3, which has been previously computed. Well, but let's have a look at the template. Again, everything is based on a template folder, CFD, which needs to be prepared manually by the users before actually executing the simulations on the cloud. Now you can recognize the three folders which have to be generated for every OpenFOAM case: the zero folder, the constant, and the system. The zero folder has the boundary conditions and the initial conditions information for your simulations. The constant folder has the modeling, the fluid modeling, so we're going to use an incompressible fluid modeling in our case. And the system folder contains all the other information such as numeric schemes, algebraic schemes, and also information about the number of iterations to be done and the frequency we are going to use in order to save the timestamp. So for instance, if we enter into the zero folder the U file, which is the velocity conditions, I can actually see that I'm initializing it to be 0, 0. So everything is quiet at the beginning. At the walls, obviously we imposed a fixed value, no moving walls. We have an impeller wall, which again defines a non-moving wall. Inlet is actually a pressure inlet uniform velocity situation, so we just use that. And the pressure outlet is called an inlet outlet. This boundary condition avoids backscatter flow, so avoids the flow to the turbulence to re-enter the domain from the outlet. Well, we can actually see the pressure, because this is a pressure-based simulation. Obviously, at the wall, we are imposing a zero gradient, but we are imposing two different values of pressure at the inlet and at the outlet. At the inlet, we impose a zero pressure, so P initial, and at the outlet, we impose a 100 Pascal pressure, let's say. So by using this pressure difference, we want to, let's say, the unknown the simulation is going to give us is the flow which is passing through our domain. In our domain, we use a multi-reference frame. It's actually due to the fact that we don't have enough time to perform a transient simulation. We are actually perform a steady state simulation in which the rotating part is computed by simply using what's called also a frozen rotor. So nothing is actually rotating. We are computing though Coriolis and centrifugal forces into the rotating part of the domain. In OpenFOAM, to do that, you need to set up these multi-reference frame files in which you define a cell zone, which is actually rotating, and you define the origin, the axis, and the omega. In this case, I just, to control everything in one single place, I just define three variables, one for the origin, which is 0, 0, 0. One is the rotating axis, which is along the Z axis, and one is omega, is 150 radians per second. It is equivalent to 1,500 RPMs in our case. Well, let's have a look at the control dict, which is another peculiar file. Well, what's peculiar is that we need to specify the application we are going to use. It's SimpleFOAM, which is an incompressible solver in OpenFOAM. And then in here, I just specify the total number of iterations. In here, I just running it for 500 iterations, just because I don't want the simulation to be too long in order not to make this webinar, let's say, excessively long. But what is nice is that we are going to see all the mesh generation and all the simulations time live during, let's say, our webinar. So this is quite good for us. And we are writing results, so we're writing all the fields variable computed every 100 iterations. So that's quite good in order to get also information about the evolution of the simulation. Well, now in theory, I can just run the new script, run CFD. But before doing that, I just want to have a look at the situation of the meshes which are computed on the cloud. Well, let's enter one of them. You see the simulation is actually snappy execution is over, but we are still there are still few things which are automatically computed, like check mesh and then the end reconstruct power mesh and stuff like that. So we can wait, let's say, for these simulations to be over, or we can tell our script to wait. Why not doing that? Well, using the cloud HPC exec, we have a command which is wait, and we just have tell our script to wait for this simulation, the 25968. All right. So before executing the next command, our script is waiting for this simulation ID to be completed. Well, in our case, we need to wait for all the simulations 68, 69, 70, 71, 72, and 73. So let's wait for all of them. Sorry, I go back to in here. So 68, 69, 70, 71, 72, and I think 73 is the last one. So let's have a look. 1 second. So 70, 72, and 73. All right. So we need to wait for all this simulation to be completed before actually have the possibility to execute the simulation using run CFD. Well, in this way, our, let's say, script is configured in a way that it is going to wait for all these simulations ID to be completed before actually executing this CFD. So it's going to wait for the mesh to be over before actually executing CFD simulations on these meshes. So now it's nice because we don't need to do anything over here because everything is going to be made automatically. We just go back to the cloud HPC and well, we just have to be sure that these simulations, these meshes are going to be over. So in a second, yeah, system shutdown, this simulation is going to be over really in a second. And then as well as all the others, I guess. Let's go to the last one, which probably is gonna be over as well. Okay, you see, as the simulation are completed, as the mesh generation is going to be completed, all the status of the running analysis will turn from running to completed, as it is logical to be. Okay, so we will just wait a little bit for our, let's say, simulations to be over. You see, step by step, they are all turning into completed. And our command over here is going to capture it and execute it. Let's just wait a few seconds for this to be done. Yeah. You see, they are all finishing almost at the same time. Yeah, the geometry, the mesh size generated is not that different from one to the other. Actually, there is also a report over here of the cells generated by each simulation. I tried not to make the meshes too big, so they are about 2 million cells. You can see this is the number of cells as the snappy iterations are computed. Okay, so we have 2 million cells each, 2 million cells for each mesh. So let's go to the last one. It's going to be quite similar. Yeah, roughly 2 million cells per each generated mesh. In here, as you can see, now we got this command. It says that this simulation is over. So step by step, it's going to control all the other simulations to detect if and when they are over. Okay, and once it, let's say the simulation is over, it gets the signal of that particular mesh is over, it will control the next one. So one by one, it is controlling all the meshes. Okay, when they are over, when all of them are over, you see now the second one has been controlled. When they are all over, all right, it will run the CFD command as well. So we just have one mesh which is still under computing. Actually, it's over that as well. All right, so in here, another feature, while we wait for that to be over, it is always possible to see the SnapEx mesh log file. It's here, all right, and it is present at runtime, so we can actually have a look also at the logs actually produced by Snappy. Okay, so let's go back in here. So 70 is about to be controlled. Just this time, since I manually controlled that all the meshes are over, let me just do this. I just execute the simulations, okay? Otherwise, it's just a matter of time, okay, that these checks are going to be performed. So yeah, now I'm running the CFD simulations. So executing the run CFD command, I'm executing all of them one by one. So this time a new folder named Impeller -CFD 0, 1, 2, 3, and so on and so forth is generated on the cloud. And to that folder we are copying the mesh, okay, coming from what we generated before, okay, and there it is. We have the new simulations running now on the cloud. So if I just refresh this page, I now have all my new simulations available on the cloud. They are, you see, instantaneously now they are in running mode, and in the storage everything is organized because I have now actually the 6 directories of the 6 geometries of the impeller. So again, for every simulation, okay, we are generating the virtual machine on which the simulation is going to run. Okay, so thanks to that, you can execute the simulations. Okay, while the CFD is computed, let's have a look at this post-processor, because that is a little bit peculiar. Okay. In fact, for this type of simulations, we want to get a quick post-processor, a quick overview of the results of the simulation. So we are not actually entering really the flow field into the details, sorry, but we are just measuring integral quantities such as the inlet flow, the outlet flow, the inlet pressure, the outlet pressure, or the torque produced by the flow on the impeller. Okay, so the torque the motor needs to provide to the impeller in order to generate the movement of the flow. Well, to do that, we use the function objects available in OpenFOAM. Some of these function objects are, I wouldn't say mandatory, but are recommended just to have an overview of the flow and a quick feedback if the simulation is proceeding all right. So this CellMax provides us information about the maximum velocity, pressure, and temperature in our domain. So that is actually just to monitor if the velocity is not exploding or the pressure is not assuming unphysical values. Then we have this y plus function objects, which is generating the y plus variable, which is very useful just to control the quality of the mesh and the wall resolution of your mesh. This generates a new variable, which is the magnitude of the velocity. And this is another very important function object, because this is a monitor of the flow rate at the inlet and a monitor of the flow rate at the outlet. As we said, our flow is a pressure-driven flow, so our unknown variable is actually the flow rate, and I'm monitoring it at the inlet and the outlet just to be sure that they are consistent. Since the simulation is incompressible and we are in a steady simulation, we want these two flows to be equivalent. Actually, they are with opposite sign, because at the inlet the flow is entering the domain and at the outlet the flow is going out from the domain. This is the residual plot. In OpenFOAM, this is how you do that. Wall shear stress, which is actually useful to get an idea of where we actually generating the highest part of the torque of the forces. And this is another useful thing in order to monitor the torque, in order to generate the forces of the impeller. Okay, so in here we have generated a force variable on the impeller, center of rotation and pitch axis we are using to calculate the torque generated by the impeller. And again, two more monitors to get a patch average of the pressure and total pressure, okay, at the inlet and at the outlet. So thanks to this, you can get an idea of what is the pressure at the inlet and the pressure at the outlet, which is something we know actually, but again, I suggested to do it as a monitor, okay, to verify that you are getting your results as expected. Another thing which is good to monitor is the total pressure. Okay, we expected it to increase between the inlet and the outlet. Sorry, just drinking some tea. Okay. So in our post-processing, we are just going to use these data, which are produced by OpenFOAM. We just download it and we convert everything into a CSV file, which can be opened in Excel in order to evaluate the most efficient geometry configuration of our impeller. So how we do that? Well, I generated already a script. Sorry. Well, again, everything starts with an array which tells which geometry configurations we need to evaluate, a loop, a cycle, and yeah, this time it's a little bit more tricky, this script, but I'm scrolling it quickly. This is just, let's say, a little bit more tricky because we take the data produced by OpenFOAM post-processing folders and we turn everything into a result.csv file. So I'm just scrolling. I'm not going into the details of this script, as this is not the purpose of the current configuration. But if you write us an email, I can share with you the content of this folder and the content of this script, so you can run it on your computer to make a test. All right? Obviously, once again, before running this script, we have to make sure that our simulations, our CFD simulations are over. So let's just refresh the page and let's enter one of the simulations which is going to run. let's see what's happening. Yeah, so actually, as while we had a look at everything, the simulation actually started. Yeah, so everything was ready. By double-clicking this tail.log file, I can actually have a look at what is happening. Well, as you can see, it's in the CFD part, and the simulation is actually iterating. So we are nearly at 100 seconds iteration. This is one of the cases, but I have all the others which are actually in the computing phase. I'm just monitoring the first one and the last one, because probably the first one is the one which is more ahead with the computation, and the last one is the one which is a little bit behind. It has to catch up the others. In fact, this one, it has arrived at 40, almost 50 iterations. But as you can see, iterations are proceeding quite quickly. Yeah, again, if I just refresh this page, I have some monitors which are produced at runtime directly. Obviously, there is a log of the OpenFOAM, so I can monitor it also here. And I have also all the function objects I generated before, each of which is actually producing a graph which I can use to monitor the simulation. I get some more tea, sorry. Okay, so I have the forces which are going to be monitored. Inlet pressure, which is obviously 0, that's what we set. Outlet pressure is 100 actually. I can see the line because it's down here, so it is consistent with the input data we set up. You see the flow at the inlet. We start from 0, obviously. We set the simulation to start from a 0 velocity. And step by step is going to reach a sort of steady values. At the outlet, it's the opposite way around of this graph. Okay, we are reaching a positive flow because it's going out of the domain. This is the monitor of the residuals to get an idea of the convergence of our simulation. Y plus. This is good because we need to monitor Y plus to be within certain limits in order to get a feedback on the quality of our mesh comparing to the turbulence model we are using. And yeah, that's it. As you can see, we are already at 300 time steps. Let's see also the other one. It's a little bit slower. It reached about 200 time steps. Yeah, as I told you, okay, you can see also the convergence of the inlet flow rate has almost reached. It is about 0.8 meters cube per second. Okay, so that is the computed flow rate at the inlet. That probably won't change much now. And yeah, so step by step, I'm just going to wait for these simulations to be over. Obviously, I need to wait for these simulations to be over before executing the post-processing. So just wait a second for these simulations to be over. A good thing is that I'm just going to show you this. While the simulation is running, I can open ParaView by double-clicking the ParaView icon here at the bottom. When it loads, I can just open my simulations. All right, and since I'm running it on a decomposed par file, I'm just opening it. I can maximize to full screen this window. And now it's like my computer is actually the virtual machine on which the simulation is performed. All right, in here I can actually have a look at what is actually happening into my impeller. Okay, I can actually have a look at the flow quantities. So I can actually have a look at the flow, at the velocity. I can actually have a look at the turbulence to get an idea where more turbulence is generated So that is probably where we need to act in order to reduce the turbulence. And obviously I can generate slices of my domain. Let's move towards the bottom and let's press apply. All right, so this is the pressure, okay, right at the outlet. As you can see here, we have a very high pressure, then it suddenly decreases. So in here for sure there is a pressure drop which needs to be fixed. Sorry. Again, I can actually have a look at the velocity in order to monitor the velocity quantities, for instance, generated by my simulation. In the meantime, this simulation has come to an end. So step by step. Also in here, we are running a reconstruct part to reconstruct the solution after the simulation is completed. Okay, as you can see, I can have an overlook at the residuals. Obviously, we haven't achieved full convergence for this simulation, but running a full convergent simulation would take longer than the hour of the length of a webinar. Okay, so I just wanted to give you an overview of what could be done. And yeah, you can see we performed 6 scenarios at the same time, and step by step they are coming to an end. So I'm finishing them. Sorry. Yeah, so also this one is almost over. It's uploading files on the storage. And yeah, if I now enter the storage and just enter any of these folder, I can see that the content of this folder has now all the time steps computed, and obviously I have all the logs of the operations performed. I have the post-processing where I have the function objects which operated. So yeah, it's like I run the simulations on my computer. The only difference is that it runs on the cloud, alright? So I use the cloud HPC exec tool in order to communicate with the cloud. Yeah, also this simulation is going to be over soon, and I'm just waiting for, let's say, all the simulations to be over before running the post-processing file. With that, I can actually see the results of my pumps and upload these results in Excel and run my own evaluations of these variables. So let's have a look at the running analysis. So step by step, I'm entering them. You see, it's quite flexible because while I keep, let's say, this window open, which has a list of all the simulations I performed, I can enter the details of each single analysis. So this one has been completed while I open it. Let's go to the second one. All right, this is about to be over. All right, also the iterations came to an end. Okay, so that's quite good. This simulation probably is a little bit slower than the others. I just double click tail log to see what's happening. Yeah, we are at about 500 iterations. So in a minute or two, this is going to be over as well. And this simulation file is over. Okay, so system shut down. It means that also this is turning into complete soon. So we just need to wait for this analysis to be over, which is probably the one with the biggest mesh among the 6 simulations performed. So if I just refresh this page, I'll be able to see that only one analysis now is going to be missing to my simulations to be completed. I don't see questions in the chat, so I just carry on with the analysis. it's worth a while now just having a look at the virtual CPU hours. That is, let's say, the computation time we rented on the cloud. As you can see, for the meshing phase, we just computed 3 to 4 virtual CPU hours. For the simulation time, we just used 10, 15 virtual CPU hours. So keep this number in mind because every CPU hours is assigned a cost, and you will see that eventually the overall cost for the use of these 6 cases is very, very little. So yeah, as you can see, just one simulation is pending, is running actually, but that simulation, let's say the simulation is over, it's just uploading files on the cloud. So let's wait a little bit for it to complete the files upload to the cloud, and then I'll run the post-process. I'm sorry, it is taking some time, let's say, and basically we are waiting for these simulations to be over, but everything is made real time. So all the computations of the mesh and of the CFDs is real time, okay? Just to give you an idea of how long actually a simulation can take to be computed, and also to give you an idea of the fact that I'm running all these analyses simultaneously, so at the same time. Yeah, you can get really an idea on how long it can take you to run 100 cases at the same time. Yeah, this case has been computed as well. This running is going to turn into completed. And when it does that, I'm going just to execute the post-process. So I just prepare for the post-process to be executed, /post-process. Yeah, I just wait for this to be completed, and then I just press enter, basically. It's just a matter of seconds, I think. All right. As you can see, if we had to run all these simulations one after the other on my local computer, well, it would take quite a long time, because now we computed them in 20 minutes maybe, and on my local computer it would take more than 2 hours to do the same thing. Okay, so that's the horizontal scalability we saw before. So now we're running the post-process. Automatically the system is downloading files. It is extracting the information from these files, and this for all the impellers that has been computed. So again, I'm not doing anything actually. I just executed a command at the beginning of I just entered the terminal the command to be executed, and yeah, and everything is made automatically. So let's just wait for the computation, for the download phase to be over. Yeah, here it is, there it is. So if I now refresh here, I can actually see that I generated this results.csv file. I just double click it to open, and I'm opening it in Excel. There it is, Excel, it is now opening. And in here, I have the integral quantities of the 6 impellers I just generated, okay? You can see every impeller has a different flow. So if I need an impeller with the highest flow, I would take the 4th case. All right? Instead, as far as the, let's say, torque is concerned, well, obviously the 4th case is the one with the highest torque. We need also to compute efficiency, but having the torque and having the flow at the inlet and the pressure difference between inlet and outlet, it is easy to compute the efficiency. So we can decide to pick, for instance, the most efficient impeller. Okay, so you see, very easily we get an overview of the situation of the 6 impeller we generated, and we can pick the one which is most suitable for our needs. Okay, so having this Excel, we just know which geometry is the best one for us, and we can take that. Well, I go back to the presentation. All right, as I was saying before, let's have a quick overview of the costs of the cloud. Keep in mind that every simulation, every single mesh and CFD simulation used, let's say, roughly 20 virtual CPU hours. So we performed 6 simulations, so we used 120 CPU hours to compute these 6 geometries, 6 meshes. Every CPU hours has a cost which starts at 4 eurocent. So I can say that roughly the cost of this mesh and CFD generation of all the geometries was 4 euros, because we used about 100 CPU hours. So it's a very cheap cost considering the computational resources we used in order to compute these geometries. The pricing is a little bit more complex because there are discounts for sustained use, so it is possible to generate several, to get a cheaper discount, a cheaper cost rather than the ones prescribed here. But you know, this gives you an overview of the costs of the cloud computing. We have a question by Korai. Thanks for the question. Did you use solid impeller instead of extracting flow volume, or SnappyX mesh did it? That refers probably to the geometry I was using. The impeller was actually, one second, I'm hiding the geometry. The impeller was actually just a 2D made of buffers, basically. I had the inlet and the outlet parts. Okay, so the inlet part was actually connected to the inlet edge of the impeller, as well as the outlet, which was connected to the outlet edge of the impeller. The geometry was actually linked perfectly to these two inlet tube and outlet tube, let's say. And I also, actually didn't tell you before, I also had a rotor, which was just a cylinder containing the impeller geometry, which I used to specify the multi-reference frame. Or in case of transient simulation, I can use everything which is inside of this cylinder. I can place it in rotation. Snappy was using this data and using also this rotor to define the portion of the volume which is actually rotating. And the impeller and the STL file generated from the impeller was actually defining the boundary also in Snappy. If you want, under the mesh, we can have a look at the Snappy. You see, I'm reading the STL of the impeller, which is just basically a baffle. I can actually see the rotor STL, which is right over here. And if I go a little bit far down, obviously I have the refinement of the impeller, and for the rotor, I'm using the definition of a cell zone directly in Snappy. Obviously, I repeat it again, this is, let's say, the template of Snappy. I'm just replacing every time the impeller file with the impeller 1, impeller 2, impeller 3, with all the impeller geometries I generated from the CAD. This was actually a good question, and probably it's because also Korai is an advanced user of Snappy and OpenFOAM tools in general. I invite Corey, but I invite everybody here to get in touch with us via email. Here I give you the email address. I invite you all to register to the Cloud HPC website. It is possible to use for free the application up to 300 CPU hours just for testing if everything is actually suitable for your needs. And testing that is helpful in order to see if actually you get a speed up of your simulations, of your cases, of your analysis in general, and if it actually is possible for you to use it, the web application. So I invite Corey and everybody else here in the platform to register. It's for free. You don't need anything else rather than enter a form details and you receive credentials to use the web applications. I also get another question by Raffaele Magni. If it is possible to see the templates folder, yes, it is possible. Just send me an email using the here reported email address asking for the templates folders, and I'm gonna send that to you. I prefer not to add this to the comments of this video, just because I'm sending it via WeTransfer, and so the link has an expiration date. So probably via email I can just send you a new WeTransfer link, which is valid for 1 week from the moment in which you receive the email. Thanks, Roberto, for the congratulations. Yeah. So from my side, it is everything. I'm very happy of you all taking part to this webinar. And I invite you to follow the LinkedIn channels in order to get updates of new webinars. And I thanks also to all the people who took part to the poll. And for sure, we will follow the polls in order to decide what to do in the next phases. Once again, thanks you all for being part of this presentation, and see you soon on Cloud HPC. Bye.